This is the Crank Car Grand Prix by MEM 435 Team 6, group members Michael Liberati, My Fan, Michael Rulo, Shane Mims, and James Ostman. The natural science we are aiming to teach with our product is the science of magnetic fields and induced currents, known as Faraday's Law. The applied science is the generation of power from magnetic fields via induction. Specifically, when the magnetic field is manipulated, the induced current will change proportionally. Pictured in this slide is a Creo model of our final product concept. The concept includes two adjustable cranks which connect to a slot car track. The idea of the product is that two users will adjust the distance between the coils and magnets on the crank as they please before spinning the cranks, which provides power to the slot cars. Based on the current output, which will be visible on a multimeter attached to each crank, the cars will move at a speed proportional to the power output. The users will notice as they move magnets farther away from the copper coils, the current output shown on the multimeter will decrease, and the speed of the slot cars will change. This will introduce them to the concept of Faraday's Law and induced currents. There are two main crucial functionalities for our product, both causing a difference in magnetic flux. The first is adjusting the distance between the magnets and the coils, where a greater distance produces a lower current output. The second is varying the speed of the rotor, measured in revolutions per minute, where a higher speed produces a higher current output. These crucial functionalities relate directly to the stakeholder needs we have identified for this product. This slide contains an image of our prototype. It consists of a crank assembly, a rotor with magnets, a stator with copper coils, and a multimeter to measure output. As the crank is turned, the magnets rotate and induce a current on the coils. The distance between the rotor and the stator can be changed by moving the crank assembly away from the stator. This will cause a change in current output. Our physical prototype is different from what was initially designed. The magnet assembly was rotated 90 degrees in order to induce the current. The initial design did not produce a current. The gears were eliminated from the design due to a material issue with the plastic gears. Different wire for the coils was needed because the enamel coating on the wire initially purchased prevented conductivity. The light bulb was eliminated due to output limitations. The multimeter serves as the sole measurement of the output of this prototype. Experiment 1 tested different distances between the rotor and the stator. It was tested at a set speed of 1000 RPM at distances of 0 to 2 inches in increments of 0.5 inches. Experiment 2 tested different speeds at a set distance of 0 inches. The speeds tested were 250, 500, and 1000 RPM. This slide shows our results from the previously described experiments. In the process of making this prototype, we encountered issues, primarily with our materials. The ceramic coating on the wire prevented continuity, which also prevented measurable induction in the wire loops. The gears should also be made of material other than plastic, which failed during testing. Also, the crank assembly needs to be redesigned with a more optimized gear ratio. The orientation of the magnets needed to be changed in order to induce a current in the wire loops. The design of the stator needs to be changed to accommodate the new orientation of the magnets. Due to issues making and testing the prototype, the math performed is inapplicable due to the errors with the wire and the coil orientation. The prototype made meets the requirements set by the Franklin Institute, but not in its current state. This product should not be developed in its current form. Although the intended concept was proven, redesigns are needed to address the issues mentioned in the previous slide. The following are videos of our prototype. The first video shows the rotator attached to a cordless drill to achieve speeds of 1000 RPM. The second video shows the failure of the plastic gears of our original design.
Trevor.
This concludes our presentation. Thank you for your time and attention.